Well, hello physics students, and welcome to this video lecture that is going to kind of debrief some of the things that we saw or that we should have seen in the virtual collisions lab, formally introduce you to conservation of momentum, and also use if charts to help us understand conservation of momentum a little bit more. So what I have up here is a situation that we should have seen in that virtual collisions lab, where we have two objects moving towards one another, they collide, and then they move away from one another. So what I'm going to do here is, yes, we have a system of two objects here, but what I'm going to do in these first two if charts here is I'm going to draw those if charts for the individual objects. Okay, so starting out with object 1, we can see that object 1 is moving to the right and it has some mass, so it has a positive amount of momentum. So I'm just going to mark here V initial 1, and I'm going to mark that it has some mass M1. Okay, so it has some initial amount of momentum. Now finally, after that collision, we're seeing that it's moving in the opposite direction. So it still has momentum, but that momentum is in the opposite direction. So I'm going to mark this V final 1, and again it has some mass 1. That doesn't change, okay? So we have some final amount of momentum and it's negative. So now we have to ask ourselves, well, how do we go from having positive momentum to negative momentum final? Well, we have to have a negative impulse, right? So, and that should make sense, because if we look at this collision here, the force that object 1 is experiencing is from object 2. And object 2 is applying a force in the negative direction. So I'm going to mark this on here. I'm going to say force of object 2 on 1, and it happens in some amount of time. And there we go. Okay, so that's our complete if chart for object 1. Now moving on to object 2. Again, with these if charts, we're just trying to document what's going on initially, finally, and that helps us understand which direction that impulse actually is. Okay, so for object 2, initially it's moving to the left. So it has some amount of negative momentum. So I'm going to mark here, I'm going to say this is V initial 2. And again, V initial 2 has some mass. It looks pretty similar to object 1, so it'll look something like this. Okay. Finally, momentum flips. Object 2 is moving in the positive direction. So I'm going to mark this here as V final 2. And again, it has that same mass, M2. So there we go. Okay, now finishing this if chart up, well, if we're going from a negative amount of momentum to a positive amount of momentum, we have to have some positive impulse, okay, caused by a positive force. So again, if you look up here, the force that object 2 is experiencing is from object 1, and it's directed to the right. So I'm going to mark this. I'll say F1 on 2. It happens in the same amount of time. So there we go. Okay, now what I'm going to do with this final if chart here is I'm actually going to be combining each of these if charts, okay, for object 1 and object 2. So what that's going to look like then, it's not too groundbreaking, but we'll say that we have V initial 1 has that mass 1, so we have that positive area. Then for object 2, we're going to say, okay, we have that initial velocity, and we have some mass. All right, so there we go. There's our initial chart, our velocity versus mass graph for this system of objects now. Okay, now we're looking at the system as a whole. So now moving to the final amount of momentum, we're doing the same thing. So V final 1 has mass 1. There we go. All right, and then V final 2, again it was positive. All right, so there we go. Okay, so you see all I did here is I just combined these two together into one chart. Okay, now this is the important part here. If I combine these two impulse charts, what do I end up getting? I end up getting 0 for an impulse. Okay, end up getting 0 for an impulse. Now, why is that? Well, first we can go back to Newton's third law and we can say these forces are equal and opposite to one another. So essentially they kind of negate themselves in this system. But more importantly, what we want to think about, and relating back to last unit in work and energy, these are internal forces within this system. An internal force within a system is not going to change the amount of momentum that we have. Yes, these individual forces are going to change the amount of momentum that these individual objects have and change the direction maybe that momentum is in. But because we have a pair of internal forces here, they're doing nothing to change the amount of momentum that we have initially and finally. Okay, so just focusing on this if chart now, we can write a conservation of momentum equation. So we can say m1 v initial 1 plus m2 v initial 2 plus, well, our impulse here is just 0, okay? And that's going to equal then m1 v final 1 plus m2 v final 2. All right, and now we can solve for a bunch of, we can solve for any one of these variables that we see here now, based on this equation. So again, just using the if charts as we have been, but now we're actually able to use them within a system. And the key here, and this is always going to be the case, our impulse in a system of objects is always going to be 0. That means that regardless of what type of collision we're working with, our momentum initial is always going to equal our momentum final. Okay, so on the next slide, I'm going to go through a kind of a sample problem incorporating an if chart, and then I'll formalize our definition for conservation of momentum. All right, so here's our sample problem here. We have a 4 kilogram meatball moving with a speed of 6 meters per second, and it's moving towards another meatball which is at rest. So kind of a silly example, but the key here is that these two meatballs collide and stick together. And what we're looking for is the final velocity of this two meatball system. So to create our if chart here, the initial velocity of that 4 kilogram meatball is 6 meters per second, and it has a mass of 4 kilograms. Okay, so we have some initial amount of momentum for that 4 kilogram meatball. And then our 2 kilogram meatball, we still want to document the mass here, but that 2 kilogram meatball is not moving. Okay, so really our initial amount of momentum in this system is only dependent on the 4 kilogram meatball. Now finally, these two things collide and stick, so that means that they're both going to be moving at the same final velocity. So that 4 kilogram meatball is going to be moving at that velocity, and our 2 kilogram meatball is going to be moving at that velocity. I hope I do a very good job. There we go. All right, now here's the important thing once again. These two meatballs are applying forces to one another, but again, those forces are internal to this system. So that means that within this system, there is no impulse because there's no external forces acting on these two objects. It's just those two objects applying forces to one another. So before we even set up an equation, we can see that our initial amount of momentum in this system is just the area of this right here. It's 24. So we know that if we have 24 kilograms times meters per second of momentum here initially, that's what we have to have finally. All right, but I'm going to write out our equation here. Anyway, so I'm going to write out the full equation. So we're going to have 6 times 4 plus 2 times 0. Okay, so 6 is the mass of the meatball that's moving. That's the velocity of the meatball that's moving. Mass of the meatball that's not moving. All right, and that's going to then equal the mass of the moving meatball plus the mass of the meatball that was at rest times our final velocity. Okay, so now if we do this math out, we're going to get a value, v final, of 4 meters per second. Okay, so that means that the two meatballs together are moving at 4 meters per second. All right, so again using these if charts just helps us document how much momentum we have initially and final. And I really think in cases, in terms of conservation momentum, it's very useful to see the relative sizes of these areas to know that, okay, well, if that 4-kilogram meatball collides with the 2, it's obviously going to be moving at a slower velocity than it was initially. So I like to try and be a little bit obvious about making these sizes, particularly for the 4-kilogram meatball, smaller than what I had initially. Because what we want to kind of see here is that these two areas added up should be relatively close to this initial area. Okay, that's the whole key here, because the area of these velocity versus mass graphs, that is the momentum within this system. Okay, so, oh boy. I'm going to try and make everything smaller here. Okay, so to summarize conservation momentum, what we're saying is that regardless of the type of collision, whether it's perfectly elastic or inelastic, that the momentum that we have initially equals the momentum that we have finally. And that is because, and this is assuming that there are no external forces acting on the system, but the internal forces, the interaction between those two objects, it does nothing to change the amount of momentum initially and finally. Those internal forces result in an impulse that is equal to 0, because those two impulses that act on the individual objects, they basically just cancel out. Okay, so moral of the story here, regardless of the collision, momentum is always going to be conserved. But you should have seen in that virtual collisions lab that it is only in perfectly elastic collisions that KE and momentum are conserved. Okay, so oftentimes I could ask you a question. You could look at a collision and I could ask you, what type of collision is this? And a good way for you to tell is you can just, momentum is always going to be conserved, but you can compare the amount of kinetic energy initially in a system and the amount final. And if those two don't match up, you know that collision has to be inelastic, because it is only in perfectly elastic collisions where both KE and momentum are conserved. All right, so there's conservation momentum. It's a big topic in this unit, and we're going to be working with this a lot, but also continuing to work with just the basic ideas of momentum and impulse. We're going to continue using these if charts because I think it's a very good visual for us to document amounts of momentum initially and finally for just one object, but also for a system of objects as we just saw. So with that being said, take care, physics students, and have a good rest of your day.